You are watching the Quick Start Guide for the automatic sample changer for the BioSAXS 1000. You'll need access to certain materials to complete this Quick Start Guide. A Rigaku HSA standard kit, refrigerated microcentrifuge, PCR strip centrifuge, 0.2 milliliter PCR tubes in strips of 8, 1.5 milliliter microcentrifuge tubes, tube sealing foil or tape, ultra-pure laboratory-grade water, 70 to 100% ethanol, and pipetters and tips. First, prepare the HSA standard. The Rigaku HSA standard kit comes with an HSA buffer tube and an HSA protein tube containing 10 milligrams of protein. Begin by removing the parafilm from both tubes. If the HSA protein is not all at the bottom of the tube, give it a quick spin in a microcentrifuge. To make a 20 mg per ml solution of HSA, add a half a milliliter of HSA buffer to the HSA protein tube. You can flick the tube to try to suspend the HSA protein. Then use a pipetter to ensure that all of the HSA has been suspended. Next, spin the HSA sample in a refrigerated microcentrifuge for 15 minutes at 10 to 15,000 times G. While the spin is going, please make your way over to your BioSAXS 1000 control computer to get set up for data collection. The next section covers the initialization of the BioSAXS 1000 and the ESC. On the control computer desktop, double-click the SAXS icon to open the SAXS software. Click on the Instrument Control menu and click on Initialize to open the initialization panel. In the panel, click on the following options: Detector, Pin Diode, Shutter, Sample Changer, and Temperature Control, and click Initialize. Initialization should only take a few moments. You can follow the progress of initialization by observing the messages that are being displayed in the bottom left corner of the SAXS interface, and in the top left corner you can observe the spinning ball animation. When the animation stops and the message is complete at the bottom left-hand corner, you know initialization is finished. Next, start the water chiller and set the temperature of your sample block. Go to the right side of the SAXS interface, enter a data collection temperature, and click Start Controller and set temperature. Notice for this example, we're using 21 degrees Celsius. Next, find the center of the capillary flow cell in X and Y coordinates. It's likely that a system administrator or log notebook already has the X and Y coordinates that you're looking for. For example, our system log notebook has X equals 7.2 millimeters and Y equals 0.5 millimeters. We're going to go ahead and rescan anyways, just to be certain. In the Align Sample tools, first scan using X by clicking the X radio button. Then input the fixed value for the Y coordinate. Then input the range of the scan in X. Normally, use a millimeter below to a millimeter above the target X position, and click Start Scan. The sample holder moves into position, the X-ray shutter opens, and the scan begins. When the scan is complete, you have a plot of beam intensity versus sample position on the x-axis. The plot shape is essentially a valley. The middle of this valley is the center of the flow cell capillary. Clicking in the plot will create a dashed vertical line that will show you the precise x-coordinate for the middle of the capillary. Make note of this position for later use. Also, make note of a background x position about 1 millimeter above the center position. Next, we're going to scan in the y-axis, so click the Y radio button, input the value of x that was just determined, and input a range of scan for y. Usually the Y scan range is larger than the X scan range, so we change the step size and the custom radio button to a value of 0.2 and then press Start Scan. When the scan completes, click in the plot to find the center of the peak and determine your Y coordinate position. Next, make your way to your instrument and make sure that all the wash bottles are full for the ASC. The first wash bottle should have ultra-pure water, the second 70 to 100% ethanol, and the third ultra-pure water. Next, recover your HSA protein from the centrifuge and serially dilute it. To dilute HSA, set a pipetter to 150 microliters and prepare 3 empty microcentrifuge tubes. Then, pipette 150 microliters of HSA buffer into each of the 3 tubes. To make a solution of 10 mg per ml HSA, make a 1-to-1 dilution by taking 150 microliters of the 20 mg per ml HSA solution and adding it to the next tube containing 150 microliters of HSA buffer. Make sure you pipette the solution up and down to mix it thoroughly. Repeat the process of 1-to-1 dilutions to make a 5 mg per ml and a 2.5 mg per ml solution of HSA. Next, transfer the HSA, protein, and buffer to a PCR tube strip. Label the strip from left to right: buffer 10 mg per ml, 5 mg per ml, 2.5 mg per ml, and then repeat the sequence to finish out the 8. Make sure to transfer 70 microliters of the appropriate solution to each of the tubes. When finished, use a strip of adhesive foil or tape to seal the top of the PCR tube strip. Then give the PCR strip a quick spin to eliminate any bubbles introduced by pipetting. Now you're ready to put your samples into the ASC. Open the blue cover to your ASC. Locate the foam cover of the sample block, remove it, and place it on the blue cover. Get your samples, place them securely in the sample block, and replace the foam cover. Then close the blue lid to your ASC. Now you are ready for automatic data collection. In the BioSAXS Lab interface, click the Collect task on the top of the screen, and then click the Read Scans button towards the bottom of the screen to open Windows Explorer and locate the schedule we'll be using to collect the HSA data. You need to go to C, Rigaku, BioSAXS Lab, Schedules, and in this folder you'll find the schedule we're looking for, ASC_quickstart.csv. On Linux systems, you'll find the schedule in a different location shown on the bottom of the screen. Once you've selected the schedule, click Open to load the schedule into BioSAXS Lab. The data collection schedule is not yet complete. First, you have to enter the coordinates for the capillary center and a background position. Start by going to the first row in the sample X and Y columns and enter the coordinates for the center of the capillary in X and Y. To fill the same value throughout the entire column, select the entire column, right-click the first row, and select Fill Down. Now grab the scroll bar and move the schedule until you see the columns for background X and background Y. Here enter the X and Y coordinates of a background position. Normally, one value larger than the capillary center in X, and the same value for the capillary center in Y. Now you can start data collection by clicking the Collect Scans button at the bottom of the screen. When data collection completes, you're ready to process your data with BioSAXS Lab. BioSAXS Lab works on multiple user platforms. Here we're going to use the Macintosh version of BioSAXS Lab to process the HSA data that we collected. On the desktop is the HSA_example output directory. Inside the directory are all the images collected for HSA buffer and HSA protein. In addition, we have a silver behanate powder standard image that we're going to use for calibration in BioSAXS Lab. Launch your BioSAXS Lab software. When the software opens, go to the right and click the blue arrow to minimize the help instructions. Make sure you're in the Calibrate task by clicking Calibrate at the top. To open a silver behanate image, click the Open folder on the right. This will open a file list where you can select your silver behanate image and then open it by clicking Open. Silver behanate has characteristic powdered fraction rings that occur at specific d-spacings. This information is used to calibrate the sample to detector distance and direct beam position by clicking the Calibrate button. The red rings should overlay with the powder diffraction rings, and you'll see a crosshair for the position of the direct beam. The calibrated values are listed in the sample to detector distance and direct beam position X and Y dialogues above. The calibration information can be stored as an XML file. Click the Save Disk icon to do this. Click the Generate from Image button to see if the calibration worked. This converts the image from pixel space to Q space. In Q space, all the diffraction rings should become vertical lines. To process the HSA data, click the Processing task at the top. To load those images that represent buffer plus HSA protein, click the top left plus icon. Select all the protein concentrations using 2 mouse clicks with the Shift key held. Click Open to load them into the interface. All the images are immediately converted to one-dimensional plots that appear in the plotting window. For buffer, repeat the process using the lower plus icon. The scattering intensity of the buffer should be less than that of the protein plus the buffer. You toggle back and forth between the sample curves and the buffer curves using the buttons at the top of the plotting window. The scattering intensity of the HSA protein should vary proportionally with the concentration of the protein. The 2.5 mg per ml at the bottom, 5 mg per ml in the middle, and 10 mg per ml at the top. Save all the curves by clicking the Save Selected button. This saves everything that's currently selected in blue. Next, average the data for the duplicate concentrations of HSA. Select both 2.5 mg per ml concentrations, click the Average Selected button, and click the Save icon to save the average curve. Repeat the process for 5 mg per ml and 10 mg per ml. Scroll down in the window and click on all 3 average curves to see what they look like in the plotting window. Next, average the HSA buffer curves by using the same steps. To subtract the HSA buffer out from the protein samples, click the Enable Sample Subtraction checkbox at the bottom. Automatically, one curve from the top window and one curve from the bottom window are selected in blue. You can change these by clicking on them. Right now we're looking at the 2.5 mg per ml buffer subtracted data in red. If we click in the list of concentrations, we can observe the 5 mg per ml and the 10 mg per ml buffer subtracted data. To save the buffer subtracted data, click the appropriate curve in the sample curve window and then click the Save Disk icon at the bottom. To view the Kratky plots for HSA, click the Kratky plot radio button at the bottom of the plotting window. The Kratky plot here is shown in red. The sample and buffer curves are still shown, and you can turn those off by clicking their names. You can look at the Kratky plots for the other concentrations as well by doing the same steps. Remember, a well-formed peak in a Kratky plot is evidence of a compact, properly folded protein. To examine the Guignay plots, click the Guignay plot button at the top. The Guignay plot is a plot of the natural logarithm of the intensity versus Q squared. It's focused on the lowest regime of Q, and there should be a linear region there, which is called the Guignay region. You get the radius of gyration from the slope of this line. The intensity at zero scattering angle is determined from where this line crosses the y-intercept. And you can toggle the fitting here by adjusting the minimum Q value and the maximum Q value that are used in the linear fit. Remember, the Guigne approximation is only valid to Qmax times Rg equals less than 1.3. Going back to the one-dimensional processing, we can select the other concentrations of HSA and examine their Guigne plots as well. Record both the radii of gyration and I0 values for all three concentrations of HSA. In your favorite spreadsheet program, tabulate all of the values for Rg and I0 versus concentration. The Rg value for HSA should be 29 to 30 angstroms. Also calculate the I0 divided by input protein concentration. This value should be constant for a protein concentration series that has no concentration effects. All of the data files we saved during processing can be found in the HSA_example directory. Two new directories are there, curves and averaged. In the curves directory, you'll find .dat files for every image we collected. .dat is a standard format for most SAXS data processing programs, containing columns for Q, intensity, and the error in the intensity. You can open these files and process your data elsewhere if you like. In the averaged directory, you have the average.dat files, and in the subtracted directory, you have the buffer subtracted.dat files. This concludes the Quick Start Guide for the ASC.